History is often perceived as a predetermined sequence of events, unfolding inevitably. However, this perspective overlooks the profound impact of hypothetical, sudden changes. Consider a catastrophic scenario. What if Earth's rotation abruptly ceased? The immediate consequence would be immense, unprecedented global devastation. Furthermore, if the sky remained perpetually still, never moving again, this thought experiment highlights the fragility of our existence and the non-inevitability of history. Earth's rotation is a fundamental characteristic established during its formation. Approximately 4.5 billion years ago, the early solar system's dust and gas coalesced. Conservation of angular momentum caused this protoplanetary disk to spin. This persistent motion defines Earth's dynamic existence. Earth rotates eastward, completing one full rotation every 24 hours. At the equator, this rotational velocity is approximately 1,670 kilometers per hour. The rotational speed gradually decreases as one moves towards the poles. At the Earth's poles, the rotational velocity becomes zero. Earth's rotation is a fundamental astronomical phenomenon shaping our planet's environment. The most evident consequence of this rotation is the rhythmic alternation of day and night. As Earth spins on its axis, different regions are continuously exposed to or shielded from sunlight. The side facing the sun experiences daylight, while the opposite side is enveloped in night. This predictable pattern dictates the biological rhythms of nearly all life forms on Earth. It also profoundly influences human activity, scheduling work, rest, and social interactions. Earth's rotation significantly influences global weather patterns, extending beyond the day-night cycle. The Coriolis effect, a fictitious force, arises from this rotation. It deflects moving air masses and ocean currents, altering their paths. This deflection creates large-scale circulation cells, distributing heat and moisture globally. Ocean currents are crucial for marine ecosystems and regional climates. These currents are significantly influenced by the Coriolis effect, a rotational force. The Coriolis effect drives the formation of massive ocean gyres. These gyres redistribute warm and cold water across the globe. This redistribution regulates global temperatures and nutrient cycles, impacting marine life. If Earth were to suddenly cease its rotation, catastrophic events would unfold globally. The atmosphere, due to its inherent inertia, would continue its eastward motion. This continued atmospheric movement would generate winds of extreme velocity. At the equator, these winds could reach speeds up to 1,670 kilometers per hour. Such immense speeds would cause widespread devastation across the planet. Hypervelocity winds represent an extreme atmospheric phenomenon with devastating power. These winds possess sufficient force to strip away any object not securely anchored to bedrock. Buildings and critical infrastructure would be unable to withstand such immense pressure. All living organisms would face immediate obliteration under these conditions. The impact would transform structures and life into a maelstrom of debris. This debris would then be propelled across the planet's surface, causing widespread destruction. A sudden halt in Earth's rotation would trigger catastrophic global events. One immediate consequence would be the generation of colossal tsunamis across all oceans. The immense rotational momentum of the oceans would not cease with the Earth's crust. This inertia would cause vast volumes of water to surge uncontrollably. These powerful surges would inundate continental landmasses, reaching far inland. The devastating force of these tsunamis would fundamentally reshape global coastlines. Cities, especially those at lower latitudes, face the most severe devastation from extreme kinetic energy. The immense kinetic energy released by atmospheric and oceanic forces would be catastrophic. This energy would render urban areas unrecognizable, leading to widespread destruction. The aftermath would leave behind a landscape of utter devastation, obliterating existing structures. The Earth's crust would experience immense stress from instantaneous deceleration. This sudden stress could trigger unprecedented seismic activity across the globe. Widespread earthquakes would occur as a direct consequence of this violent adjustment. Volcanic eruptions would also increase significantly due to internal structural shifts. The planet's internal structure would adjust violently, leading to catastrophic geological events. The Earth's rotation generates a centrifugal force that slightly counteracts gravity. This centrifugal force is most pronounced at the equator due to the greater rotational speed. Consequently, perceived gravity is marginally weaker at the equator compared to the poles. In a hypothetical scenario where Earth's rotation instantly ceased, this centrifugal force would vanish. The absence of centrifugal force would lead to a subtle increase in perceived gravity. This increase would be particularly noticeable and measurable in equatorial regions. Tidal locking is an astronomical phenomenon where an orbiting body's rotation period matches its orbital period. This causes one side of the orbiting body to perpetually face its primary, while the other remains unseen. A common example is Earth's moon, which is tidally locked with Earth, always showing us the same face. If Earth were to become tidally locked with the sun, one hemisphere would face constant daylight. Conversely, the other hemisphere would be plunged into eternal darkness, creating extreme temperature differences. This scenario would drastically alter Earth's climate, weather patterns, and potential for life. Tidal locking causes one hemisphere of a planet to experience perpetual daylight. This constant exposure to the sun leads to extremely high, scorching temperatures. Conversely, the other hemisphere remains in permanent night, without sunlight. This results in frigid, uninhabitable cold conditions on the night side. Tidally locked planets exhibit extreme temperature differences between their day and night sides. The day side experiences immense heat, while the night side remains perpetually cold. This significant temperature differential creates a powerful driving force for atmospheric movement. Consequently, persistent global winds are generated, flowing from the hot day side to the cold night side. These winds are crucial for redistributing heat across the planet's atmosphere. The result is a highly dynamic and turbulent atmospheric circulation pattern unique to these worlds. The Coriolis effect is a fundamental force influencing global ocean currents. Without this effect, ocean currents would cease their familiar circulation patterns. Instead, the Earth's gravity would pull all ocean water towards the poles. This gravitational pull would result in the formation of two massive polar oceans. Consequently, a vast land bridge would emerge along the equatorial regions. The Coriolis effect is crucial for maintaining the Earth's current oceanic distribution. In certain planetary environments, life might be restricted to specific zones. This concept applies to planets with one side always facing their star, creating perpetual day. The opposite side experiences perpetual night, leading to extreme temperature differences. Life, if present, would likely be confined to a narrow twilight zone, or terminator line. This region exists between the scorching day and freezing night sides of the planet. Here, temperatures are moderate enough to allow for liquid water and support an ecosystem. Even within the twilight zone, conditions for survival are extremely precarious. Significant atmospheric pressure differences characterize this harsh environment. Constant and powerful winds further contribute to the relentlessly challenging conditions. These extreme environmental factors severely test any form of biological adaptation. The combination of pressure and wind creates an environment where life struggles to persist. Civilizations in the twilight zone must adapt to a static solar environment over millennia. This environment fundamentally alters their perception of time. Their understanding of direction would also be profoundly changed. Even the concept of gravity would be subject to alteration. These shifts necessitate the development of entirely new ways of life. Earth's rotation is crucial for maintaining its magnetic field, generated by the geodynamo effect. A non-rotating core would disrupt the complex mechanisms that produce the magnetosphere. This disruption could lead to a significant weakening or even collapse of the magnetic field. A compromised magnetosphere would expose Earth to harmful solar radiation, impacting life. Earth's magnetic field is crucial for protecting our planet from solar winds. Solar winds are streams of charged particles emitted by the sunday. Without this protective field, solar winds would strip away Earth's atmosphere. This process would occur over geological timescales, leading to a gradual loss of vital gases. Such a loss would make the Earth's surface hostile to life, as seen on other planets. The absence of centrifugal force would alter a planet's gravity distribution. Earth, currently an oblate spheroid, is flattened at the poles and bulges at the equator. Without centrifugal force, Earth would gradually transform into a more perfect sphere. This shape change would trigger significant geological shifts and adjustments across the planet. Planetary rotation is crucial for long-term planetary stability and dynamic processes. Without rotation, Plate tectonics, a key geological process, would cease or drastically change. Weather patterns, driven by atmospheric dynamics, would also be fundamentally altered. The planet's magnetic field, essential for protection, would be significantly impacted, leading to a different geological future. The existence of complex life forms is contingent upon specific planetary conditions. A profound transformation of these conditions poses a significant threat to life survival. This highlights the delicate balance required for a planet to sustain complex life. The current rotational state of a planet is not a mere coincidence. It is an integral factor directly influencing the world's habitability. Changes to rotation can drastically alter climate and environmental stability, impacting life. The world we inhabit is not a fixed or inevitable reality. Its existence and current state are products of countless variables and historical contingencies. There was never a guarantee that our present circumstances would unfold as they have. This understanding highlights the fragility and preciousness of our established order. It underscores the continuous effort required to maintain and shape our collective future.